Assalamu alaikum warahmatullah. Welcome to my class on distributed and parallel computing. Please don't forget to subscribe to my channel, my YouTube channel, to find all new videos. Okay, for today, our class actually is going to be all about the parallel programming models. So after we learn about the parallel architectures, now we need to know about the parallel programming to develop or to be able to create applications or programs that can run over parallel architectures to get the benefit of the parallel architectures. The first thing here, we have the outlines. So we have the overview, then we have shared memory model, then trace model, and after that we have message passing model, then data parallel model, and at the end other models that are not so common. There are several parallel programming models in common use. Actually, there are shared memory model, threads model, message passing model, data parallel, hybrid, and parallel programming models exist as an abstraction above the hardware and memory architecture. So whenever we use that programming model, that programming model actually is going to use the abstraction of the hardware to deal with the hardware in a proper manner. Even if the hardware changed, then the program doesn't require that too much changes. Sometimes does not require any change. So this is the main concept of the abstraction. And here we have some points that are still related to the overview. So although it might not seem apparent, these models are not specific to a particular type of machine or memory architecture. So all of that models are working on any type of architecture, but always when we deal with parallel programming, we need to take care about many things, actually, including the hardware that we have. Sorry, guys. In fact, any of these models can theoretically be implemented on any underlying hardware. So theoretically, there is no issue. You can use, for example, trace model over shared memory architecture, and also you can use it for distributed memory architecture, and vice versa. So you can use whatever model on whatever architecture, theoretically. Okay. Shared memory model on distributed memory machine. For example, this one actually is one example, which is the Kendall Square Research KSR all cache. This is an approach of the shared memory model on a distributed memory machine. Okay, this is very well known. Okay. Here, machine memory was physically distributed but appeared to the user as a single shared memory. Actually, the user here is the programmer. The user here is the programmer. So the machine memory was physically distributed, means the memory is distributed physically in different places, maybe on different machines or whatever. Okay, but to the programmer or the user, it will be seen as a single shared memory or global address space. Generically, this approach is referred to as virtual shared memory. Virtual shared memory. Why virtual shared memory? Because physically the memory is not one piece, is not one memory space. It's distributed on multiple machines maybe, or on multiple pieces of physical memory. Okay, but the user or the programmer can see it as a one virtual shared memory. Okay. Note here, although KSR is this Kendall Square Research, although KSR is no longer in business, actually it's not available now because no longer in business, there is no reason to suggest that a similar implementation will not be made available by another vendor in the future. So why they say this? Because this model or this approach has no problem actually with it, theoretically has no problem. So maybe in future, maybe other vendors could bring it back to the market. Okay. Because as we said, any approach or any model of parallel programming can work over any type of architecture, supposedly to work over any type of architecture theoretically. Yes, and how it works, this is the responsibility of the programmer. Okay. Then here we have something called message passing model, MPI, on a shared memory machine. On a shared memory machine. So here we have MPI on SGI origin. Okay. The SGI origin employed the CC NOMA. So this one is non-uniform architecture. Okay. Non-uniform memory access architecture with coherent cache or cache coherency. So here the SGI origin employed the CC NOMA type of shared memory architecture where every task has direct access to global memory. So in this case, all tasks or all threads actually going to access directly the global memory. Why? Because here we are still under the shared memory, okay, not distributed memory. So, however, the ability to send and receive messages with MPI, as is commonly done over a network of distributed memory machine, is not only implemented but is very commonly used. So this model actually is very common, the MPI. Okay, the MPI is very well known. When we talk about parallel computing or distributed computing, what comes to the mind directly is the MPI. Okay, and the MPI, as I explained yesterday, it's an open source library that's available online for free. You can download it, you can install it, you can modify it. It's up to you. Which model to use is often a combination of what is available and personal choice. Yes. Why? Because we cannot say that a certain model is better than the other. We cannot say trades model is better than shared memory model. We cannot say that. It could be depends on the application, could be depends on the programmer, could be depends on the company, could be depends on whatever. Okay, so the choice is the programmer's choice. Okay, there is no standard to say that, for example, threads model is better than shared memory model, or faster, or less overhead, or we cannot say that. Okay, there is no best model, although there certainly are better implementations of some models over others. So here we cannot say that model is better than the other, but the implementation of a certain model, we could have multiple implementation for the same model. and that implementation could one could be better than the other. Depends on how complete is that library or that implementation. Okay. The following sections describe each of the models mentioned above and also discuss some of their actual implementations. Okay. In the shared memory programming model, tasks share a common address space. Why? Because they have a global memory space, That's why all tasks will share the common address space, which they read and write asynchronously. Okay, so everybody can read from the memory, can write from the memory to the memory asynchronously, without synchronization. Okay. Then here, an advantage of this model from the programmer's point of view is that the notion of data or ownership is lacking. Why? Because here, for example, task 1 have some variables in the memory, task 2 has some variables in the memory, task 3 has some variables in the memory, and that memory is global and shared. So when we see that variables, we cannot differentiate them. We cannot know which one belongs to what task or which one belongs to the other task. Okay, because they are in the same pool inside the global shared memory. So there is no need to specify explicitly the communication of data between tasks. So program development can often be simplified. So here, because of that reason, when we do programming, we don't need to specify the task or how to bring that data from that task or something like that. It's directly we can access that needed data from the memory. Okay, even though if that data belongs to another task. Various mechanisms such as locks, semaphores may be used to control access to the shared memory. Okay, so here to control or to protect the data from being damaged, especially if two tasks try to write the data at the same time, so it could be damaged. Okay, the data could be damaged or could be written in wrong way, then it will give a wrong result and so on. So to avoid that from happening, we can use locks and semaphores. So that looks is like that. For example, if let's say, let me open the paint. If let's say this is the memory here, and for example, we have variable x, and x here equals to, for example, 1. Okay, then for example, here we have T1, task 1, and task 2. So for example, task 1 wants to write a new value, for example 2. And here, task 2 wants to write a new value, for example 3. So if the two try to write at the same time, what will happen to x? X will be equal to 2 or equal to 3. We don't know what will happen. How the value is going to be written, we don't know. The important thing that we are sure will happen is that the value of x will be wrong. Okay, because two tasks try to write at the same time, so the value will be something mixed between the 2 and 3, because the value will be saved as a binary. So it may take some parts from the value 2 and some parts from the value 3, and then finally the value become like maybe 30 or 20 or something else, which is totally wrong. So that's why if let's say we have this kind of concurrent access to the same data in the memory, then what we have to do is to apply locks. So for example, these two come, then the organizer, the scheduler need to know which one is going to be first. So for example, if the scheduler decided that the T1 is going to run first, then this one actually is going to be delayed. Okay? The scheduler will tell task 2, please wait until task 1 finish. So task 1 here actually, before it write, it will apply a lock to the variable. Then it will write or override that value. Then after that, unlock the variable and finish. Then task 2 is going to be able to update the value of the variable x. Okay, so also task 2 is going to apply a lock, then override, then after that unlock. So maybe if there is a task 3 need to access, after that it can access, and also task 3 need to apply lock, and so on. The problem of lock actually is the source of something called deadlock. Deadlock, very well known problem which affects the operating systems and many parallel programmers that have multiple tasks that can run concurrently and can access the same data in the shared memory. So here, any one of you guys knows about the deadlock?
Yes. Is it the banker's algorithm?
Yeah, that's one example could be that, and actually the problem in general, there is something called the philosopher's problem. So last time they formulate the problem like that. So suppose that we have a plate of pasta here, okay? Then here we have, sorry, what was it? Here we have, La ilaha illallah. Here we have this forks, okay? This very basic example for the to explain the deadlock. Suppose that here is some people are sitting here and willing to eat that pasta, okay? So here is the philosophers sitting here and want to start eating the pasta. So we have one condition actually to make this work as a deadlock. They assume that no one can eat with only one fork. So for every person sitting here on the chair on the table willing to eat that pasta, that person need to use 2 forks at the same time. Otherwise, one fork cannot eat. With one fork, he cannot eat. Okay. So if let's say here we started at the time 0, then every person here take the fork on the right hand, for example. So this guy will take this guy will take this guy will take this, and that guy will take this. Then all of them are going to be waiting for each others to release one of the forks to let them eat, right? Right, guys, or not? So
Yes.
this guy actually number 1 is waiting for number 3, for the guy number 3 to release this fork to allow him eat, right? And number 3 is waiting for number 4 to release the fork to allow him eat. Number 4 is waiting for number 2 to allow him eat. Number 2 is waiting for number 1 to allow him eat. Okay, so here what we do, or what schedulers do actually, or what controllers do, is to release when the deadlock happen, especially in the operating systems. If the deadlock happen, they will come to the low priority task and enforce her to release the resources, and here the fork is the resource. So this fork could be variable x, this fork could be variable y, this fork could be variable z, this fork could be variable w. So maybe this program here needs variable x and w to achieve the task. And variable x is available, but variable y or w is locked by this person, number 4, or by the program number 4. This is 3, this is 2, and this is 1. So in this case, if the priority of program number 1 is higher than the priority of program number 4, then the system will, the scheduler will ask the program number 4 to release the variable w. Then program number 1 could continue working and finish the task, and after that it will release x and y. Then later program number 4 can still work with the w. Okay, is that clear, guys?
Yes, Doctor.
Yeah. So in here, this thing actually reflects the, or describes the shared memory. Okay, and those people representing the programs or the tasks that we want to run to achieve some tasks. Okay, so here if we don't have a scheduler, to decide which one is to be enforced to release the resources, then this deadlock will be forever, and the system will enter something called starvation situation. Starvation means no food, right? So all tasks will be in the starvation mode, and all of them will never finish, and all of them will continue waiting for each other forever. Okay, then the system will hang, and the user will be angry. Then maybe we decide to restart the computer or whatever to make it refresh, to see or to find our applications responding again as normal. Yeah, this is what happened actually when the system hang. So you see, you open like 2-3 applications, then everything hang because some applications require some parts of the data from the memory, then they cannot get it because it's locked by others, and everything stopped. Okay, it's not all the source of all problems actually, but this is one of the common problems. In the very common operating systems like Windows, Linux, Mac, they have very smart solutions to handle this kind of problems. But when it comes to parallel programming, the programmer need to handle this case, which is one of many cases that could happen when we talk about parallel programming and concurrent implementation, or concurrent, running of tasks. Okay, so the programmer is the number one responsible to apply the locks or waiting strategies or whatever to handle this kind of cases. Okay. Then here, an important disadvantage in terms of performance is that it becomes more difficult to understand and manage data locality. So it's very hard to understand the data locality because data is coming from many tasks and saved inside the global memory space. So maybe the schedulers or the system, the operating system, does not know the locality or cannot understand the locality of each variable. In this case, it will not be able to handle the cases of deadlocks, to enforce some tasks, to release the resources, and so on. So that's why it's very important for the programmer to be careful when it comes to concurrent tasks. You have to be careful. You have to know what kind of techniques you need to implement, and when you need to implement the technique, for example, X or technique Y. Okay. On shared memory platforms, the native compilers translate user program variables into actual memory addresses, which are global. This is one of the basics. So I think it's very clear. No need to explain it. No common distributed memory platform implementations currently exist. However, as mentioned previously in the overview section, the KSR all-cache approach provided a shared memory view of data even though the physical memory of the machine was distributed. So here, from this point, we will know that there is no common distributed memory platform implementations currently exists. Okay. There is some individual works. Yeah, there is some individual works, but there is no common distributed memory platform actually available like the other implementations for the distributed memory architectures like MBI. MBI is very well known, so it's available and everybody is using it. Okay. To recap, we already finished the shared memory model, right? Shared memory model. And now we will come to the thread model. Actually, threads model is very important, very important. And threads model is one of the most used approaches or models to implement or to develop parallel programming. Okay. So in the threads model of parallel programming, a single process can have multiple concurrent execution paths. Okay. So in the parallel programming, one process, guys, can have multiple concurrent execution paths. So it could run in different directions concurrently at the same time. So perhaps the most simple analogy that can be used to describe threads is the concept of a single program that includes a number of subroutines. So the thread, actually, to be run, we have to create the thread. Then we have to assign a subroutine or a function to that thread to allow it to run separately or independently. So here, based on this example, you can see here the arrow of the time. So the execution starts from up to down. The main program is a.out, this one. A.out is the main program, is scheduled to run by the native operating system. So a.out loads and acquires all of the necessary system and user resources to run. Okay, so here, as you can see, we call sub1, call sub2, do this, assign that, whatever. And then we call subroutine 3, we call subroutine 4, and so on. So as you can see here, the main program, the main process, could start creating other threads to run subroutines. So this one, subroutine number 1, is going to be run through the thread number 1. Subroutine 2 is going to be run through the thread number 2. Subroutine 3, thread number 3. Subroutine 4, thread number 4, and so on. So as you can see here, we have how many lines of execution? We have this one is the main line, and thread 2 is the second line. Thread 1 is the second line. Thread 2 is the third line. Fourth line, fifth line. So we have 5 executions concurrently running on the same machine. A.out performs some serial work. This kind actually of execution is serial, but that serial creates some parallel execution, right? So always the start point of any program must be serial. We have no choice. Any program in this world, even from very big vendors like Microsoft or maybe Oracle or whatever, even if it's parallel program, it has to start serially. It has to start sequentially first. So the start point of any parallel program is sequential. Then from that point of sequential execution, we could see the concurrent threads starting to come to the scene to execute parallel tasks. Okay? So here, A.out performs some serial work and then creates a number of tasks threads that can be scheduled and run by the operating system concurrently. Each thread has local data, but also shares the entire resources of A.out. This saves the overhead associated with replicating a program resource for each thread. Each thread also benefits from a global memory view because it shares the memory space of A.out. So here, to explain, those threads actually, every thread is a subroutine or a function. So that subroutine or function could have its own private variables inside that are declared inside the function or inside the subroutine. So that variables will never be able to access from outside or from other threads. Even from the main program, it cannot access it because that kind of variables are private or internal. Okay, but also they still share the common memory, and they could access the public variables that are declared by the A.out or by the main program. Okay. Also, that shared memory or the common memory that's declared by the main program, actually it could include many variables to be accessed by the threads. So threads could call back the main program. They could call back the main program to inform anything happen during their execution. Okay. So for example, let me use this one. For example, if let's say this is program, this is the main program, for example here, and here is a creation of thread, and here is another creation of thread. So this one is thread number 1. So it will continue like that. And here we have a thread number 2, which will continue running like that. So here, if let's say in this main program, we want to know the progress of T1. What's the progress of T1? Is it, for example, 20%, 30%, 50%? We don't know, right? Because this one actually is going to be independently executing or running on the processor. Okay, so that program will have no idea about what is happening inside that subroutine. So for that reason, we could create, for example, t percentage, for example, variable, and we assign 0 here, for example. Then when the task here in thread number 1 arrives at the execution point here, we could assign 20%. So how to assign the 20%? We can go back using the callback and we update this variable and we set 20%. So this main program will know that the thread number 1 is now achieved 20%. So if let's say we reached here, maybe 50. So we update 50. And maybe when we arrive here, we update 100. So after this 100, then this thread actually will be or must be killed or terminated by the main program. Okay, so this kind of updating the shared memory is called callback. Callback. It's a kind of communication to update the main program about what is happening in the subthreads. Okay, is that clear, guys?
Yes.
Okay, theoretically the concept is easy, and also for the implementation, for me actually is very easy. I consider that very easy. A little bit complicated compared to normal programming, but when you have the enough time to understand or to implement or to try that concepts, you will understand how it works and when you need to use it and how to use it. After you make that comprehension, everything will become easy, guys. Okay, so this is the main concept. Actually, in the slides there are a lot of theoretical things. I want to continue because the exams are shared between this group and the other group. That's why I have to cover what we have in the slide. But at the same time, I always try to give you something that could help you when you start developing your parallel application or parallel program. So these concepts are not available in the slides, but I explained here to allow you to let you understand how is the concept. Okay. Okay. In the threads model of parallel programming, a single process can have multiple concurrent execution paths. As we said, here we have how many execution paths? We have 5. So the main one and the 4 threads. During this line of this point of time here, there are only 3 execution lines, right? There are only 3 because here we have 1, 2, 3. But at this point of time we have 4 because now we have 1, 2, 3, 4, and here we have 5. But here we have 3 only. Okay, so it depends on when you call the subroutines or when you start your threads and when you kill that threads. So this will decide how many lines of executions you have concurrently. A thread's work may best be described as a subroutine within the main program. So any thread can execute any subroutine at the same time as other threads. So threads communicate with each other through global memory. As I said, they can communicate with each other through the global memory that's declared by the main program. This requires synchronization constructs to ensure that more than one thread is not updating the same global address at any time. So here, they have to implement something called synchronization technique, which is could be waiting technique, or could be look technique, or many techniques actually. Okay, we have many techniques. So every thread should implement that technique to avoid having multiple threads updating the same piece of data in the memory. Okay, threads can come and go, but a.out remains present. So here, this is the main program, and this main program has the ability to create some threads and kill them after they finish their task. So the threads come and go, right? As you can see here, we have 2 threads, here we have 3, here we have 4, then we come back also to 2, and after that 1, then at maybe a certain point here later, we could have 0 threads, only the main program is running, and so on. Okay, so threads could come and go, but the main program is always available until we close that program. Okay? Threads are commonly associated with shared memory architectures and operating systems. I don't want to comment on this point. Yeah, let us move here. So threads model implementations, how to implement. So for example, is suppose that we have machine A and machine B. So machine A sends data to machine B. So here, from a programming perspective, thread implementations commonly comprise a library of subroutines that are called from within parallel source code, a set of compiler directives embedded in either serial or parallel source code. In both cases, the programmer is responsible for determining all parallelism. Okay, this is the main point here. Okay, threaded implementations are not new in computing. Historically, hardware vendors have implemented their own proprietary versions of threads. These implementations differed substantially from each other, making it difficult for programmers to develop portable threaded applications. So this is another kind of parallel applications. So parallel threaded, portable threaded applications is not easy to develop. Why? Because it will come later to a point which is very important, of how the operating system actually abstracting the underlying hardware. Okay. So this is the main point that makes the implementation of parallel threaded applications quite hard. Unrelated standardization efforts have resulted in 2 very different implementations of threads. So, for example, we have something called POSIX threads and OpenMP. So, POSIX threads stands for Portable Operating System Interface. And it's an IEEE standard designed to facilitate application portability. It's an attempt by a consortium of vendors to create a single standard version of Unix. This is what they call it, POSIX. Then we have OpenMP. So OpenMP is called or a short form of Open Multiprocessing. Supports multi-platform shared memory multiprocessing programming in C and C++ and Fortran. On many platforms, platforms here means operating systems like Windows, Macintosh, Linux, whatever. Instruction set architectures and operating systems including Solaris, AIX, HBUX, Linux, Mac OS, and Windows. So here, they draw this diagram here in this slide to show you that the trades could be actually executed on even different machines. Okay, or maybe on different cores, or maybe on different processors, or maybe on different threads. If let's say we have a multi-threading processor, depends on the architecture that we are using. Okay, I will try to show you something if still available. I'm not sure about it in Windows 10. Yes, here. As you can see here, if you open your task manager, you can see the number of the utilization here of the processor. Definitely you need to click here on the CPU. You can see the utilization, you can see the speed, then you can see the base speed, you can see sockets, cores, logical processor, virtualization, blah blah blah, layer 1 cache, layer 2 cache, layer 3 cache. Then you can see here the uptime, for how long the computer is running, and this one is the number of processes, so which reflects the number of applications you run on your computer currently at this point of time. So at this point of time, we have 278 processes or applications, and those applications generate 3,124 threads. Okay, so you can imagine how this is about 300 processes generates about 3,000 processes. That means about 10 threads for each process, right? Then here handles maybe I think this one maybe instructions, number of instructions here. So you can see, you can imagine, we have 3,107 threads running concurrently at the same time on this machine now. Okay? So here, if let's say we take the Google Chrome, we open like that, we see how many threads we have, right? All of these are threads. So especially the common application, which is the Google Chrome. Google Chrome actually uses one thread minimum, at least one thread for every tab. One thread for every tab you open. Okay, so you can see here the number of tabs. Every tab has one thread. Then we have maybe some extensions. So in my case here, I have those extensions installed, and some of them are running. So we can see one of them is the tracker blocker host, which is coming from the internet security, the Bitdefender internet security that I installed on my machine. And also here we have Windows Command Processor, another one. So maybe this console window application maybe is the scheduler of the Google Chrome. We don't know what is that. And also we have Free Download Manager, which is also another extension I installed on my Google Chrome. So this is how in reality, how it's going to affect our system. So if, for example, if you go here and see this paint, because the paint actually is a serial program, it's not a parallel program. You cannot do multiple tasks at the same time here under the paint. That's why we see the paint has only one thread. Only one thread. But if you see here the OBS Studio, OBS Studio actually is a multitask application, so it can record your video, it can do streaming at the same time, it allows you to modify, to do some configurations, to enable some features and disable some features at the same time. So depends on what kind of features do you use on the OBS Studio, it will create the threads. Now here, because I am only opening the OBS for recording, so it has only one thread. Okay. Here, Cisco WebEx. Cisco WebEx, we have multiple threads here. So maybe this one is a meeting desktop application. This is the main application. This one is the MTA. So if you read about what is the MTA, I think the MTA is the one related to shared desktop or desktop sharing, if I'm not mistaken. Then the other one is collaboration helper, 3 threads. So maybe if we enable other feature, maybe the threads will increase. Okay. This is the main concept, guys. Here, what we still have, let us go through this before the time finish. Threads model, actually POSIX threads library based requires parallel coding. This one is a library which is also an open source and available for free. You can download, modify, whatever you can do with it. It's designed for parallel coding or parallel programming specified by the IEEE POSIX 1003.1c standard in 1995. It uses C language only, so commonly referred to as B-thread. Actually, this one is C language only because there is C and C++. C is different than C++. C is not object-oriented, but C++ is object-oriented. So why C? Because C actually can run over any type of operating systems, especially Unix. Okay, but C++ could run over certain operating systems only. That's why they make it C to make it more general, to fit more types of operating systems. Most hardware vendors now offer B-threads in addition to their proprietary threads implementations. So the name of the package now is called B-threads. Very explicit parallelism requires significant programmer attention to details. So programmer need to be always alerted. Okay, we'll stop here because time is already finished. So maybe I need to add something here. We stopped here. So we, inshallah, we continue this next week. Okay. So guys, is there any question?
So far, no, doctor.
No, doctor.
Are you sure?
Yes, doctor.